Okay, 7-4, day 1. As soon as I find something to write with, right here. Like I said, we're talking about vector forces today. And when we talk vectors, there's 2 components to a vector. They have magnitude and direction. Magnitude is some kind of force or length. And direction for vectors, not quite like bearings, but because they're from due east that's our positive x-axis, and then we go counterclockwise. So, for example, I could draw vector AB. The symbol for vector, very similar to a ray, except that it has half of an arrowhead on it. That's what the difference between ray and vector is. Because a ray is just that goes on forever, and this is a vector, which is similar to a ray because it has that direction, but it also has a magnitude to it. So vector AB is going to have magnitude 5 centimeters at 20 degrees. So if we were going to draw that, we would need a reference line, and our reference line is due east. So I like always to dot in my reference lines. 20-degree direction. So I go counterclockwise from that, 20 degrees. And then I show a length of 5 centimeters. And in the picture, it will look like a ray, but when we name it, it has that vector symbol. So, the vector is starting at A and finishing at B. That's what it would look like in a picture. So, you can use 2 letters, the starting letter and the finishing letter. Or sometimes they use it with 1 lowercase letter. Let's go vector lowercase c, which will have magnitude 2 centimeters at 200 degrees. If we were to sketch that one, we always have that reference line, which is due east. So I'll start with my due east reference. Doesn't matter how long the reference line is, because that's not the vector. So now I want to rotate 200 degrees counterclockwise. So if you think about 90s, 90 would be straight up, 180 would be just directly behind it, and then I go 20 degrees past that, just estimating. So just a little bit, and it's short. So that's a 200-degree rotation, and we'd label it vector C. Okay, so we're going to be adding and subtracting vectors next, so we'll talk about that. Adding vector forces together. They must be placed head to tail. Head to tail. Okay, think of vector forces. Say there's a big crate here sitting on the floor, heavy crate, and there's a rope tied to a ring on it, and you guys, two of you have to drag this thing across the floor. Well, if I get two people up here, one little tiny one, and then a bigger person, and they're going to pull this thing, the tiny person probably doesn't have as much force as the bigger. We put Paige up here with Megan Crow. Who's going to be able to pull more weight here? Probably Megan. So Megan, whatever direction she's going to pull that in, Paige is probably get dragged a little bit toward that. They're both going to work together, but vector forces are the different pulls. Like if somebody's going to pull harder than the other one, it's going to pull it more in that person's direction. That's what the vector forces are. So to actually see the direction, we can place the vectors head to tail. So I'm going to keep them in a simple direction so it's easier to see. So for our example, I'm going to start on the next page here so they're all together. For the next several examples, we're going to use the same vectors. Vector A is going to pull due north. Vector B is going to pull due east with a lot less force. And I show that by making it shorter. So the amount of force is given by the length of the vector. And then vector C, let's put at like a 45-degree angle, and we'll make it longer than B but shorter than A, so in between the two. So those are our three vector forces. Let's draw vector A plus B. So like I said, when you show two vectors, they have to be added head to tail. So we draw vector A first, which is due north. So I'm just trying to copy that vector. When I add vector B on, it has to be added head, meaning arrowhead, the arrowhead of the first one to the tail of the second one, so head to tail. So the tail of B gets put there. So the actual, so think of these as the two ropes. You don't have to draw this part. Don't draw this part, I was going to show you. So if these were the two ropes, Megan was pulling on this rope, and Paige was pulling this rope with less force. That's the way it would look like in real life. But what's going to happen is the crate's going to drag at this direction. The air from the head to the tail. Let me grab another color here. So what I'm going to draw now is the actual slide direction and the amount of force. That's the direction that the box will slide. Well, that came out terrible. Black one. So we show it starting at the first one, showing the arrowhead direction. That's the way the box will slide across the floor. So this black vector would be A plus B. Let's draw vector A plus C. So, this would be Megan and myself dragging this crate across the floor. So Megan's going to pull due north. I'm going to get a little closer to her and pull at this angled direction. So, and I have to add it to the arrowhead. So I'm just trying to copy that and draw it down here at the same angle, same length. That's good enough. So that's A. This is C. So head to tail, arrowhead of the first one, tail of the second one, and now the actual slide direction is this one. So you can see our vector is a little longer, which means we had more force, and our direction's a little bit more north. But the whole point is they have to be added head to tail. can all three of us pull this crate? Well, if there's 3 ropes on there, we can. So our last example, let's add A plus C plus B. So with 3 people working, head to tail. So we start with the first one, A. That's that due north one. At the arrowhead, I'm going to add on vector C, which is that angled one, 45-degree angle, about the same length as I've got up there. And then on the arrowhead of that one, I'm going to put B on. And B was this one going this way. So the end result of 3 people pulling in those directions, this one right here. From the start of the first one, you have to show the arrowhead direction at the end of it. There it is. So adding vectors is pretty simple. Head to tail, connect them, and your final vector is the start of the first one to the arrowhead of the last one. So this vector here is A plus C plus B. Good with adding vectors? Just going to be sketching some of those today. Couple of vocabs out of the way here. Equal vectors. For vectors to be equal, there's 2 components to a vector, magnitude and direction. So to be equal, they have to have the same magnitude, same direction. Now, opposite vectors. What do you think it's going to take for 2 vectors to be opposites of each other? Nope. Think about pulling. Opposite vectors, think of somebody pulling one way, somebody pulling the opposite way, so everything's staying still with equal power. So that means they're going to have the same magnitude, they're both going to pull with the same force, but pulling in opposite directions, so nothing happens. So they will have the same magnitude, but opposite directions. How many degrees do you think it's going to be between opposite directions? 180. So if we show that vector C went that way, the opposite of C is going to be opposite of C. 180 degrees in the opposite direction. And I didn't have to draw it to the tail, I could have drawn it here too. Just that it's going to have the exact same length, but pull in the 180 degree opposite direction. So, what that leads us into is subtracting vectors. Just like when you learn to subtract integers, you just add the opposite. So subtracting vectors, you add the opposite vector. So we'll use those same A, B, and C that we had. So let's draw vector A, subtract vector C. So, A was our due north vector. And I know that subtracting we just learned was add the opposite vector. So I just rewrote this as adding the opposite. So I'm going to draw the regular C. C would be this way. So the opposite of C is going to go 180 degrees in the opposite direction. Do I have to draw vector C here, the positive one? No. It just helps me get it going in the opposite direction. So now, the A minus C vector is the one that starts at A and ends at opposite of C. So it's this one there. So that black one is A minus C. Will C minus A look like the same vector? Is it commutative? Let's find out. Let's take C, subtract A, which means we're going to have C plus the opposite of A. Which tells us start with vector C. I'm going to add on positive A, then I'll do the negative A. So I'm going to add on, so at the arrowhead, A goes north. So that means opposite of A goes 180 degrees in the opposite direction. So C minus A, remember I started at C, and I go to the arrowhead of the one I stopped at. How do my two vectors compare, my two answers, A minus C and C minus A? Yeah, same magnitude but opposite direction. So it's not commutative, it's commutative. Subtraction is going to make it go in the opposite direction. So far so good? Adding and subtracting, can do that. Now can we multiply? A scalar product just means we're going to multiply the magnitude by a value k. So we're not multiplying two vectors together, we're taking one vector and multiplying it by a constant. If we were going to draw 2c, vector 2c, all we're doing, the direction's not going to change, we're just going to double its magnitude. So it's just going to have double the length in the picture. So C was that 45-degree looking vector, and I'm just going to estimate it. That was about one length of it. So doubling it, you're just doubling the length of what we had and keeping that direction the same. Half C. It's going to keep the direction about half as long as what it was. What about negative 1.5 C? What's that going to do? So the 1.5 is going to make it 1.5 times longer. What's the negative going to do to it? Flip it and go with 180 degrees in the opposite direction. So 1, and then half of it again, about that. So the arrowhead's there to show the direction. All right. and I should have this vocabulary first, the resultant is the vector that represents the sum of two or more vectors. So all of those examples we did, I'll show you right here. When we did this A plus B and then I drew in this black one is the resultant. Each one of these is called a resultant. Like when we add numbers, we call the end result a sum. When we draw in the vector, that's called the resultant vector. So I probably should have had that earlier in the note. Okay, so sketch the resultant. So you've got to know that means, oh, resultant means I've got to add two vectors together. So here's what we know. Another way to give magnitude is to put it in absolute value bars. So the absolute value of u means the magnitude of vector u, 12, you can think of it as a length. The magnitude of vector w is 20. Think of it as a length. And the theta is 27 degrees. That means that this is the angle between the tails of the vectors. Think of them as two ropes pulling, and this is the angle between them. So it's not the direction of one of them, it's the angle between the two vectors. So with those three pieces of information, we want to sketch the resultant, which means we're going to add u plus v. So we first started out like it's the two forces pulling on a crate. So here's the crate. I'm going to try to squeeze this in here. Oh, u plus w. Watch me fix that. U plus w. Yes, it is. Okay, I don't know what direction these are pulling in real life. All I know is the angle between them. So I just choose to put one of them due east. Doesn't really matter. But here's my big crate. Here's vector u, showing a length of 12. The angle between the two tails, where it's pulling on the box, is 27 degrees. So it's not a very big angle. But I know vector w is quite a bit longer. And there's 27 degrees between them. So that's what's happening in real life. There's the two ropes with the angle between the ropes and the pulling. Now we want to show the resultant. Which way is this crate going to slide? Well, you've got to add them. The proper way to add them is head to tail. So you've got, the book moves both of them. They'll take this vector w, slide it over to the arrowhead here, and they take the vector u, slide it up to the arrowhead here. Makes a little parallelogram. You don't have to slide both of them. You only need one of them. But I'll show you what the book does. So, like I said, to add head to tail, because I didn't do one, but u plus w is going to be the same as w plus u. When we add, they're going to come out the same. When we subtract, they come out opposites, but we're adding. So we could take u, slide it up to the arrowhead here. We could take w, slide it to the arrowhead here. So let w's tail attaches to the arrowhead here. Makes a nice little parallelogram. So where's the resultant here? The resultant starts at the crate and goes all the way across, right there. There's the u plus w vector. So we've got U being 12, W being 20, 12, 20. This angle, before I drew in the black, was 27 degrees. Do you remember anything about the angles in a parallelogram? Because we are going to be getting into you can see two triangles here that we're going to be solving tomorrow. But you got to remember something about the angles.
Opposite angles.
Opposite angles are congruent. So this angle is 27, this angle is 27. Could we figure out these two angles? They're going to be equal.
Yeah, because don't they all add up to 1 pair of 360?
Yes, they do. They do all add up to 360, and they're going to be equal. Or consecutive angles were supplementary. Two angles next to each other were supplementary. So if this angle is 27, the one next to it has to be supplementary to it. So to get that angle, it would be 180 minus 27, which is 153. That'll be important tomorrow. We're doing good. You got 4 more examples. Okay. I'm trying to do one of every example that you have in your homework, so you'll be able to look back. Find the horizontal and vertical component vectors for the given vector. Resultant. Okay. So find the horizontal and vertical component vectors for the given resultant vector. So here's what I know. I've got a resultant vector W, magnitude 26, at a direction of 50 degrees. So this is the resultant. It wants to know what horizontal and vertical component vectors, so two ropes that were pulling, one pulling due north, one pulling due east, that made this resultant, is what it's asking. So what you're going to do is put this on a coordinate plane so you can see it a little bit better. So 50 degrees means from due east, counterclockwise, 50 degrees. That's vector W. This is 50 degrees. And what it's asking for is what horizontal and vertical components were added together to get this. So in other words, nothing I want to use here. I guess the pencil will work. So what vector started here, moved horizontally, and then what got added vertically to that to make that. So there was a horizontal and a vertical that were added together to make this W resultant. The question is, can we find these two? This is just a simple right triangle SOHCAHTOA problem with a lot of physics jargon thrown in. So don't let all the verbiage bother you. All it is solving a right triangle. So we can use SOHCAHTOA to do that. And W is 26. So right triangles are solved very easily with SOHCAHTOA. Let's go stand at the 50. Adjacent over hypotenuse is, good review for the exam, cosine. Cosine 50 equals x over 26. Do a little cross product using sig figs. I'm getting about 17. And then if we go for the y, that'll be opposite over hypotenuse. That'll be a sine. Cross products. Uh, 20. Okay. An alternate way to describe a vector so far you know given a magnitude and a given direction. Now there's another way you can describe this same vector. If you know the horizontal and vertical components, you can describe it like that. How much over horizontal and how much vertical movement you have. So, and they use little pointed brackets so that you don't think these are ordered pairs. It's the horizontal component vector's magnitude and the vertical magnitude. So, if I give you vector, you can call it anything, G, has a horizontal of 5 and a vertical of 12. Can you find G's magnitude and direction? So it's basically giving me the two sides of a right triangle, and I'm looking for the hypotenuse length, and then what direction is that. So, here we go. So I know it has a horizontal component of 5. Added to a vertical component of 12. So G is this vector right here. And it's asking me for two things. Its magnitude is essentially its length, which we can get with Pythagorean theorem. The direction, what do I need to find to give the direction of G? The angle measure at the origin. How far around counterclockwise is it? That'll be its direction. So, magnitude is just simple Pythagorean theorem. Uh, 25 and 144 square root 13. So magnitude is 13. And then direction, we're going to have to do a little bit of trig. So if I stand here at the angle I'm trying to find, we got to pick a trig function that works with, it doesn't matter what sides we use. I'm going to choose the 12 and the 5. What trig function works with the 12 and the 5? Tangent. So we're going to set up tan of x equals 12 over 5. And how do I get the angle measure? Inverse tan. So to get the direction, we're just going to inverse tan 12 over 5. 67 degrees. Let's see, we just did that one. Okay, last one. One that we've already done. Let's see, magnitude of U is 20.5. Its direction is 118. can you write in the horizontal vertical component form? So it's basically asking you to find the horizontal and vertical sides of the right triangle. So, we gotta sketch it. 118 degree direction puts us in which quadrant? 2. So, gotta be aware of where our 118 is at. So starting from due east, there's 90. Gotta go a little bit more. So here's vector u. That's 118. This is 20.5. The question is asking for the horizontal and the vertical component vectors. So, we got to do some trig. What do I have to do first before I can do trig? Isaac? Yeah, we need an angle inside of this triangle to work with. You guys got to know something inside. So 180 minus 118 will get us that. Not that my brain was working good enough to do that. 62 degrees. Now we're ready to go with some SOHCAHTOA. Say I want to find the horizontal one first. So that will be adjacent and hypotenuse. That's cosine. Cosine 62 times the 20.5, 9.6 if I match the place value here. Then we'll do sine for opposite over hypotenuse. .1. Okay, so horizontal and vertical. Yes or no? No. If I gave you that as a horizontal and vertical, where are you going to sketch that at? Quadrant 1. Is my vector in quadrant 1? Now what do you want to do to it? Yeah. This x has to be negative to get it in that quadrant too. So even though they're magnitudes, we need direction with it. So that x was going in a negative direction. That's got to be supplied. Okay. There was a lot of stuff there, but they're real fast problems. At least that's what I'm telling myself. Alright, what do I got for you? Page 310. 7 through 37, odd. And 51 to 57, odd.